topic for ISC is seminar presentation for derivation of shear plane, shear angle, and numerical analysis. These are my team members.
Myself Praveen Pawar.
Myself Pushkar Patel.
So now come to the introduction of our topic. So then first is the difference between orthogonal versus oblique cutting. So in orthogonal cutting is a 2D model where the cutting edge is perpendicular to the cutting direction. In constant, oblique cutting is a 3D model, so which involves an implant edge common in operations like milling and drilling. Second is the primary shear zone. So this is the critical region where the metal yields and undergoes plastic deformation. The material is transformed into a chip as it passes across the shear plane under the intense pressure and weight. As you can see, here the oblique cutting and here is the orthogonal cutting. So mechanism is the shear zone thickness is typically very small, causing high strain rates and that dictate the efficiency and the surface quality of the final part. So geometric parameters and definitions. So first is the chip ratio, the relationship between the uncut thickness and the actual chip thickness. Second is shear angle, the angle of the primary shear plane relative to the cutting velocity. It indicates the thickness of the chip formed. Third is the relief angle, also known as the clearance angle. It prevents friction and rubbing between the tool flank and the finished workpiece surface. And fourth one is rake angle, the orientation of the tool's top surface. It determines the direction of chip flow and significantly impact cutting force and power. Thank you.
Now let's derive the shear angle, that is phi. So for deriving the shear angle, we need to assume that some certain things. So first one is the tool is perfectly sharp and it contacts the chip on its face or the rake face. Then second assumption is that the maximum deformation will take place on the length AB. Then the third assumption is what? Third assumption is that the no side flow is produced in this process. Then fourth assumption is that the only continuous chips are produced without built-up heat. So in this diagram you can see that BC is our uncut chip thickness and DB which is our chip thickness after the cut. So if we apply some geometric parameters on the shear plane angle, which is the shear plane angle, the shear plane angle is DAP. So if we apply the shear plane angle for the getting value, so what we get? So it is get to sin phi is equal to, here we can see the T divided by sin phi. So and same we apply for the angle DAC. So we will get the T2 divided by cos phi minus alpha. So if we equate both the equations for the phi is equal to, so we get the T1 divided by 2 is equal to sin phi divided by cos phi minus alpha. And after that we arrange or apply the cos A plus B formula is equal to cos A plus cos B, cos A cos B plus sin A sin B formula. And if we rearrange all the terms, and so we will get final equation, that is tan phi is equal to r cos alpha divided by 1 minus r sin alpha. The derivation is going to find the physical shear angle is the function of the external inputs. So for that the role of rake angle in the shear plane derivation. So as the rake angle increases or they become more positive, the shear angle typically increases as well. That reduces the cutting force and required to improve the efficiency. And the role of chip ratio, which is T by TC, that is chip thickness before cut and chip thickness after cut. That ratio we call it a chip thickness ratio. So chip thickness cutting ratio is primarily experimental indicator, and higher value of indicates the thinner chip and the steeper shear angle, which is directly associated with the superior matching performances.
Hi, myself Pushkar Patel, and now we see numerical setup and data. The first stage is the manufacturing facility is optimizing high precision turning operation for the 140 alloy steel structure. The objective is to determine the internal dynamics of predict the heat generation and tool wear during the continuous production. In this, we understand the relationship between the measurable forces and the shear angle is the first step toward the process stability. some data is given. The measured parameter is cutting speed. First one is 150 meter per minute, and uncut thickness is 0.20 mm. Deformed thickness is 0.45 mm. Tool drag angle is 12 degree. Cutting force is 1100 Newton. Thrust force is 550 Newton. Now we see the answer. First step of the numerical is we find out the chip thickness ratio R. For calculating the ratio of uncut to deformed chip thickness, R is equal to T1 upon T2, means the ratio of uncut to deformed chip thickness. T1 value is 0.20 and T2 is 0.45. It gives R value is 0.444. And second step is to find out the shear angle. In the shear angle, finding the shear angle, we have formula. We directly putting the values. Tan phi is equal to 0.444 cos 12 degree upon 1 minus 0.444 sin 12 degree. 0.444 is the value of R and 12 degree is the angle of grid. It gives values of 0.479. When it convert to tan angle, then we get the angle of shear angle of 25.6 degree. Now third step is to calculate the shear force. For shear force calculate resolving measured cutting and thrust forces onto the shear plane. In this formula, putting value directly, because the Fs is equal to 1100 cos 25.6 degree minus 550 sin 25.6 degree. It gives the shear force value 754.37. Now see last step, to calculate the shear stress. For calculating shear stress, shear area AS first, then determining yield stress. AS is equal to 0.20 into 2.0 upon sin 25.6 degree. It gives 0.926 mm square, means total area is 0.926 mm square.
Now we see the impact analysis of the role of the shear angle in the cutting process. What if we are having the high shear angle? Sorry, if we are having the low shear angle, then it leads to the high shear plane, which means the plastic undergoing the deformation, the material undergoing the plastic deformation for the longer distance. That means that we require the highest cutting force, then it requires the high consumption, energy consumption, then it generates the high yield. Then due to improper heat distribution in the tool, it leads to tool wear accelerate. And if we are having the high shear angle, then it reduces the shear plane length. That means the material undergoing the plastic deformation for the shorter length. That means not too high stresses are generated or the high heat is generated inside the tool. That means the tool wear is reduced. Then it requires the low energy consumption as well as the power consumption step. It gives the surface finish very good, because if you are having the low shear angle, then usually in that condition the chips are formed in very thin layer, which is not even circular or circular. That means they reduce the surface finish of the workpiece. But if you are using the accurate shear angle, that leads to the good surface finish. For that, we can do some optimization techniques. For doing that, we can use the liquid cooling system for the heat resistance. Then we can adjust the rake angle for balancing the phi angle. Then we can do the speed and balance, cutting speed and for balancing the operations. So these things doing up